Okay. Yeah, let's get started. Let's pick it up from where we left off last time. So last time we talked about a very fundamental model in natural language processing, which is word embedding, and we talked about this very specific algorithm that make use of co-occurrence statistics of each word, and that algorithm is called word-to-vec model. So the idea is we use the word that is in the center and try to train a classifier, essentially. Train a classifier to predict the words that are co-occurring with the word in the center, okay? So that means we get this objective function that we could optimize. Once we have this objective function, we do the same thing we did before. We take the gradient with respect to all the parameters, and then we update the parameters. Okay. This is the loss function that we discussed last time, right? So we have a list of tokens which are in your raw data. So to train word embedding, you could just use any text data that you have in any language of your choice. And then for each word, this is the main for loop. You pick that word as a center, and you try to predict the words that are surrounding that word. That's why you have the context equal to d of I plus j. J is being to the left of the center or to the right of the center, and you sum up the log probability of all surrounding words. Okay, and to compute the probability, we use the same old what's this thing called? This is called softmax function, but we softmax it over the entire vocabulary. Okay, that's what we did last time. It seems like a long time ago. Even I this morning had to look at the slide. What did I teach? And so this is what we discussed. Okay, so we're on the same page now. So what we left off with last time is this term. To compute the probability, you need to compute this term, which means you need to compute this very expensive thing. So you have to sum up over the entire vocabulary each time for each instance of the center that you got, right? So this is what, 30,000, right? So it will cost you that much, and 30,000 just this term alone. Multiply by this term. So if you want to train it on what I say, 100 million tokens right here. So it's 100 million times the size of the vocabulary, which is super large. Okay, so it's n times k, where k is kind of large, n is also very large. So you get something that's in that order, which is very expensive. We try not to do that. To try not to do that, we use something called negative sampling. So negative sampling, essentially, if you look at this term once again, right? It's the sum of what? It's the sum of the word that actually occurred in your window, this term, right? And you add the rest of it. You don't care about each individual word, how much probability it gets, right? You only care that it's the rest of it. Okay, so it's the word that you actually want to compute the probability for versus the rest of the vocabulary. So instead of computing the probability for each word in the vocab, we just compute the rest as one chunk. So to do that, then we want to use this technique called negative sampling so that we can avoid computing that entire vocabulary, okay? To avoid computing the probability over the entire vocabulary for each individual word. All right, what does that mean? So instead of having a loss function where your labels are the entire vocabulary, we change the formulation so that the input are two words, the embedding of this guy and the embedding of this guy, and then now it becomes a binary classification. So you ask the classifier whether these two words actually co-occur in the data set, which in this case, yes, because you get it from the data, right? So if we do it this way, we turn this data set into this data set, then we won't have a zero label at all. We only have one, right? That's why we call it negative sampling. So you sample the negative. If you don't sample it, that means all other words beside this one, except for this one, are negative labels. Here's how it works. So for each window, so we have this pair, right, wicket and knight, which we know co-occur because it's in the data set, right? Once you have that pair, then you sample the negatives. That's instead of using all 20,000, 30,000 words that do not co-occur, you sample 1,000. Okay, so instead of computing the probability for 30,000, you compute the probability for only 1,000. So you save 10x computation. Okay, so you sample from the vocabulary and assign 0 as a label. So you have this extra training samples. Okay. So to do that, to compute the probability now is very easy. So you have two sets of embeddings. The first set of embedding is for the word that's in the center, in this case, Vikrit. Okay? Just a reminder, our data set looks like this, right? Looks like this. Okay? So this is what I mean by the word in the center. Okay? For the word that's in the center, you you get the embedding for this word, for the center set, and you have the context set. So for compute the probability of Vikrit co-occurring with nai, you also need the embedding for nai. All right. So you have two sets when you train the model, and that's awesome. So I visualize it here. So for example, for these phone, it's a positive sample, right? Because they actually co-occur. But God and Nok Yung, we just sample from the vocab. Okay, they don't co-occur. Yeah, so far so good. Yes. Okay. And all right, so then to compute the probability, we take the dot product between the word in the center and the word that's in the context. So we take the dot product of Vikrit from the green set and God from the purple set. All right? And we do that for all, these are all the negative samples. In real case, we're gonna have like 1,000 of this, right? And for the positive sample, you have around 4 if your window size is 2. So 2 from the front and 2 from the back, okay? In real practice, we said the window size would be around 10. Okay, so for one word in the center that you consider, you compute the probability for around 140 words. 100 coming from negative samples, and the 40 come from the window. I assume that you're listening. Okay, because I should see that you're very confused or you really get it, but right now I see nothing. So I hope you are listening. Okay, I want to see one of those, and then I know how to react. Okay, if you look confused, then I can explain it again. All right, so this is for the positive sample, as in the word that's in your window, and these are from negative samples, which you sample randomly from your vocabulary. Okay? Then you compute the dot product between each pair. So you got the dot product, and then say you get this number, and this number, and this number. Then you use sigmoid function. We are our good old sigmoid function, which has really nice property because it turns any real number into the number between 0 and 1, which is good because it's probability. The probability is in 0 and 1, and again, sigmoid function has a nice smooth curve that you can take a gradient for. So that's awesome. All right, so this here, this is the probability that we could co-occur with fun. Okay, that the model computes for you, and this is the probability that we could occur with God. So we want this to be very low because it's negative sample. Same with wicked and nocule. Most likely they don't really co-occur. Then we want this probability to be very small as well. So we're gonna make this kind of error, right? Because we want this to be 1 because your target is 1, and we want this to be 0 because your target is 0, because it doesn't, these don't co-occur and these don't co-occur. Then you have the error, and that's awesome. Once you have the error, you update all the parameters that you use to compute these probabilities. What do we use? We use the green version of Wicked, right? And we use the purple version of your positive sample and the negative sample, which are these three words. So from this error that we make, from this window, right, you update the parameters of the input word, right, because which is in the center, and also the purple version of all surrounding words. And any question on this part? Because this is the picture, the cute pictorial version. Before we get to the math version, I want you to understand the picture version first, because pictures are cute. Yes, okay. The question is, this is gradient descent. Gradient descent is the algorithm that we use to use the error signal to update the model parameters. So yes, we use gradient descent for this, because this is part of the gradient. Yeah? Awesome. Again, to give you a more rigorous version, because why not? So this looks a bit different now. So right here, since we don't have to sum over anything anymore, right? Because see, we don't sum over anything. We dot product and then we sigmoid it. So this is cheap, okay? This is very cheap. So yeah, so this is cool, this is sigmoid function. And so we don't have to sum over much anymore. And we sum over this part. What is this part? This is negative samples. Okay, so we can make this smaller so that we can go faster. So we end up saving a lot of computation. Oh, yes, gradient descent. Yes, so we use gradient descent. Once you compute the probability of the co-occurrence, then you're gonna make some errors. Of course, you will make some errors because one word can co-occur with so many. Then you try to adjust the parameters using this equation. So we compute the gradient, which is the errors times the embedding. And this is the step size. We will talk more about step size today in excruciating detail. Do you know what excruciating means? It means like you're gonna be torn apart, okay? So that's what excruciating means. So it's excruciating detail. It should be so much detail that you feel like your body is gonna split into half. Sorry, that's very figurative. Okay, so yes, so now we can update a single parameter, and for word embedding, we actually use this equation like upright. We don't use other fancy stuff, and it worked really well. Okay. That's all about word embedding. Yes. Yeah. The loss. Okay. Mm-hmm. Okay. I also posted the slides. If you. Oh crap. Okay. I thought. Okay. I thought I uploaded a new version. Still corrupted. Okay. James, can you try to export the slide again and make sure the equation look okay, and then re-upload? Thank you. Yay. So sorry about that. The PDF. Yeah, the PDF. So, do you want the spreadsheet version, or we're good? I have the spreadsheet version to train the embedding. Did we go through this last time? We did not. Let's do it. We have time. Okay. All right. So this is the same training set, the same toy training set that I show you. So in this training set, we have windows equal to 2, right? Because we look at the words in 2 in the front, 2 in the back, and this is without negative sampling. Okay. So without negative sampling, so you see that we have to compute the probability for the entire vocabulary, just so that we can compare it against the label. Okay, so let's go through this so that it's more concrete. This is the purple version that I show you on the slide. So for this we use it as part of the classifier. Okay, and V, this is actual embedding that we will use later. So let's go through an example. Suppose this set, okay, this set, wicked and knight, okay, wicked and knight. So first you choose get the embedding for the word that's input. So it's from this set, right? Okay, from the V set, not from the U set. And the U set is constant, okay? And then you take matrix multiplication between this matrix and this embedding, right? And then you get the score, and the score is not so great because it's not a probability. To convert it into a probability, you softmax it. So you first take exponential, right, of the score vector, and you compute the sum over the exponentiated score vector. And to get the probability, you take the exponentiated score divided by the sum. That's the expensive part I told you about, because in real life, this vector will be really large, and you have to compute it for each word that you iterate over in your training set. Okay, and again, you take the log probability and compute the error when compared to the truth. And in practice, you could do something a bit better, because then you can look ahead, right? That you have to do the exact same computation for other words that's in the window as well. So you could change your truth label to be like this: long, fun and ja, right? So fun and ja. So then you get the errors that you could use already, right? For all these words that co-occur. So that you don't have to do this multiplication again and again for each word in the window. So you could cheat a little bit and compute the errors for one window at a time. Okay, so this chunk, and then next iteration, you compute the error for this window, and then for this window. All right. And you do that 100 million times, as in you do it over 100 million tokens that is in your data set. So at the end, you will throw away this set. Throw out the window. You don't need to save it anymore, okay? Because the embeddings that you use is right here. Yeah, so that's training. Do I have a version for binary? Yes, I do have a version for binary. So this is a version where the first version that I show you, where we compute the probability over the entire vocabulary. And this is the negative sample version. So you can see immediately that the computation becomes so much simpler right here, right? Cool. So again, U and V is the same, but the way we use it is different because the loss function that we use is different. Okay, so this is the actual words that co-occur. These are some random things that we negatively sample from the vocab. Okay? Awesome. So where does this come from? That's from the U set, which is here, right? Because these are the words that's in the context. For the center word, the input word, we use the embedding from the V set, which is this one, right? And then we do the dot product between the two, which is awesome. And then we sigmoid that, okay? And then you see something that looks like a probability, which is cool. Okay? And then, yeah, the truth is 1, right? And then you have the error right here. This is the log probability, so I just take the log over the sigmoid function, so we can compute the error. Yeah, so far so good. And again, in real life, we cheat a little bit because then we do it for this entire thing. We don't have to actually, we can do the normal for loop, and that's fine, yeah. Yeah, so you can see that negative sampling, you simplify the computation by so much. And it turns out this thing, this is a hack. Engineering, we call this a hack because it's something that's not mathematically justified. Okay, we do it just because we tried and it worked. And NLP is full of that. This is one of the first hacks that you would see in NLP. Okay, stochastic gradient, you saw that as well. That's also a hack. You should compute the gradient over the entire data set. But in practice, we can't do that. So we compute one row and update, one row and update, one row and update. That is also a hack. Okay? Yeah, that's training for word embedding. I have a code for training, but it's just so boring because it's a library and it does everything for you. So you don't see anything at all. It's like 2 lines of code and it trained everything. So not gonna give you that. You could ask ChatGPT for that code, okay? I guess we have a little time for word embedding demo, which is pretty awesome. If it's still up. I'm not convinced that it's actually downloading. Oh, okay, good, good. Generate data set, your input message to the model. Oh, wow. That's not what I meant. Must be other demo. Hold on. Well, they don't keep this up anymore, so we don't have the demo. So we will continue to the next thing. All right. So today we'll talk about neural networks. We have seen some neural network before, right? In other, you did computer vision and all that. No. All right. So we have seen it, right? Okay. Good. Good. So yeah, one of your classmates or say that you have seen neural network already. So we're gonna go super fast. If you don't understand it, you can blame your classmate. Okay, he's right here. I'm just kidding. All right. So neural network is a very important model for AI nowadays. But we don't even call it neural network anymore. We call it AI. Okay. But neural network is a more basic term that encompasses this class of models that we now use in AI. So, oh yeah, even before AI, we call it machine learning. Okay, it's a machine learning model. Okay, so that means it's a model that learns from a large amount of data, usually large amount of data, and do something intelligent. So neural network actually have a very beautiful history, dated back to the 1950s before we have really good computers to train them. So it was just a theoretical model, which loosely based on the human brain. Okay, so it's just inspired, like, oh yeah, the human brain works like this. So since the human brain can do so many intelligent things, if we can make a model that kind of mimics the biological properties, then it should do something intelligent. This is a great idea that people came up with 60, 70 years ago and became the main thing that we do now. How does the brain work? This one cell that is in the brain is called a neuron. So a neuron is a cell that get the cells to communicate. So when the cell can communicate, it can compute stuff. That's what neuroscientists discovered. So a typical cell look like this. Okay, so this is actually a computation that will give the activation to the next thing. So we can see that this neuron is connected to this neuron. So whatever this guy get the input from. So these are dendrites. Yes, I almost forgot about that. So it receives the input from other cells, from other neurons, and it does a computation here, okay, in the cell body, and then it sends out the activation onto other cells and neurons. Then other neurons kind of do the same thing. So it becomes a network. And if you look at some part of the brain is actually organized as so. So you have a layers of these neurons, okay, say this layer, and it will send out the connection to the next layers, which is a cool idea. So you have some computation units that form a layer of sort, and it will send out the output to the next layer. So that's the idea of a neural network. So we try to sort of loosely simulate this, and to simulate this, you get something like this. Okay, so this is one layer. So you can see that this one layer, it doesn't have it doesn't have connections within the layer. Okay, kind of like this guy. It just forms a layer and they don't connect to each other. Sort of, they do. Usually they do. But yeah, in this model, we assume that in one layer, they don't connect. Okay, the neurons don't connect. So these neurons in the same layer, we call this like we call this a layer, and this is another neuron. Okay, so how does a neuron or one unit, neural network unit or neuron compute something? So we model using a very simple equation. So for the activation from neuron xi, you multiply it by the weight or the strength of the connection between this cell and this cell. Okay, so the stronger it is, the more activation of this neuron is amplified. Okay, and do the same for x2, same for x3. So each neuron, each pair of neuron has connection, and we call that a weight between the two, between two neurons. Okay, so we have input layer, we have neuron that form a layer, and we have weight between two neurons. Okay, so this become a weighted sum because you sum over the weights times the activation. So x1 times w1 plus x2 times w2 plus x3 times w3 plus the bias term, which is not in any, it's not in nature, it's in the model. Okay, it's not in the brain. We just said that, oh, you always multiply by plus b, which is the bias. So once you sum it up, so this is one unit, okay, this is one neuron. We call it a Z, okay? So you apply a nonlinear activation function onto Z, and we call that A. So A is the activation. And yeah, and then you pass it on to the next layer. Okay, so this is one neuron, and basically almost all neural networks models that we use now follow this sort of computation. To give you the math, so I give you the cute picture thing right now is the math. So we form the activation over one layer as a vector, and we also form the connection between one layer to the neuron in the next layer as the vector as well. So you, again, what do? You do dot product, okay? Dot product of the input layer and the weight plus the bias. So we can write it compactly as so. So we get Z, all right? Z is we call it the logit, okay? And then you use some sort of activation function, the non-linear activation function. It means it will look like a curve of sort, okay? To convert Z into activation. Because why? Because Z would have some uncontrolled, it will be in a crazy range. So nonlinear activation help convert it onto the right range. We have used this many times, like softmax, like sigmoid. We are using sigmoid now as the activation function. Okay, so make sure you understand all these terms, because today we'll accumulate a lot of technical terms, okay? So this nonlinear activation function, activation, and then the output. This is what? This is a sigmoid. We have seen sigmoid many times. It's curves. It got differentiated well, so you can find the gradient or derivative for this function. And it's also in the right range of 0, 1. So that's awesome. But as for now, we also use these two, but mostly the one on the left, ReLU, which is called rectified linear unit. It looks so, the name of it is insane, rectified linear unit. But if you look at the shape of the function, it's very simple. And if you look at the math as well, it looks insane. What is this thing? But basically, if it's less than 0, put it to 0. So like round it up to 0. If it's more than 0, then leave it as such, okay? That's why it looks like this thing. And technically, this is not differentiable because this part, right? So what's the derivative of this function when x equal to 0? Huh? What is sigmoid? No. The derivative of of ReLU is this thing. Okay. It should not be sigmoid because the derivative is the slope, right? The slope of this part is 1. The slope of this part is 0. So you get something like this. So when x less than 0 is 1. When x is 1 is more than 0, it's a linear function. So the slope is also 1. I think you confuse it with something else. Yes. Yes. I can prove it to you right now, right? You can take the derivative of this, right? Already 1 is like indicator function? No. As in sigmoid? I don't remember the derivative of sigmoid, yeah. Yeah, look it up. Let me know what you find out. Cool. So yeah, you can take the derivative of this. Derivative of 0 is 0. Derivative of x is 1. Okay, that's a pretty easy proof. And hyperbolic tangent, who knows what this is? But it's hyperbolic tangent. We don't use this much anymore because these two compete for a long time, and then people prefer this thing. Why do people prefer this thing? Because people use it and it works better than the right one, that hyperbolic tangent. So hyperbolic tangent just follow fashion. This is so ugly. In math, in stats, we can prove things that one is better than others. But in machine learning, in AI, we just try it many times in many settings. Whatever works best, that's the one that we're going to go for. And up until now, people still have no reasons why we use this guy over this guy, because when we use this guy, the model trains so much better. That's all, okay? So we talk about training later. Training is a lot of, like dark arts, black magic thing going on, which we'll learn some of that today. Let's talk about feed-forward neural network. Feed-forward neural network, it has an extra component. We call that a hidden layer and a hidden unit. Okay, a hidden unit is a neural unit. What's a neural unit? This is a neural unit. Okay. That done. So in standard setting, input and hidden layers are fully connected, which means each hidden unit in the hidden layer sums over up. Let me give you an example. This makes no sense. So it will look something like this in feed-forward neural net. So now you see that we have this thing called hidden layers. So the output layers, we call it output layers because they are the output. In NLP, our output are usually labels. So the output layer in this case would be the probability over each label in your classifier. Okay, so in case there are 4 labels, then the output layers will have 4 units. Okay, and the input layer usually for NLP, the input layers are usually embedding. Okay, so if your embedding has 4 dimensions, then the input layer will have 4 units plus the bias term. And here comes the hidden layer. We call it a hidden layer because it's hidden. The input you can see, right, is a text. The output you can see is a label. So what's a hidden layer? It's hidden. We don't know. That's why we have the name. Okay? So the hidden layer will receive the, so let's look at H1. It receives the input from all units in the input layer, right? Plus the bias term. All right, and then it does the weighted sum using the weight, and plus bias term use nonlinear activation function, and then you have the output that you can pass on to the output layer. Okay, and you do the same for H2, but for H2 it's a bit different. It's the same equation, a bit different because the connection from X1 to H2 and the connection from X1 to H1 are different. Okay, so it pulls in different amount of the input layer into the hidden unit. Okay. All right, so we call feed forward, from left to right, it feeds forward from the input layer onto hidden layer onto output layer. All right. To give you something more concrete, it looks something like this for WH is the weight matrix between each unit in the input layer to each unit in the hidden layer. Okay, so it would look like what? Look like this, right? 4x3 matrix, because there are 4 units in the output layer and 3 units in the hidden layers, and all the connections will have 4 times 3. Okay, or the permutation essentially, not permutation, or the combination of input layer to hidden layers. There'll be 4 times 3 connections, and we organize that in a matrix. Once you have that, then it's not hard to show that by multiplying this weight matrix and what's this guy? The input layer, right? If you multiply these, it's the same as doing this one by one. So we're not going to do that one by one. We're going to compute the activation for every unit in the hidden layer. So, and what's this guy? This is bias term. So you have a bias vector. So you have a bias for each hidden layer. For each hidden unit in the hidden layer, H1, H2, and H3. And you sum it up and you get what? You get, this is Z, okay? And once you have Z, you take whatever non-linear activation function, sigmoid sometimes, ReLU sometimes. Then you get this vector H, which is the hidden layer activation. Okay? So it activates this much. How much it actives, activation. So how active it is. Yeah, so far so good. Feed forward neural net. And then you consider this, right? So it feed forward, so the hidden layer will feed forward onto the output layer, and the math is exactly the same, okay? Now the hidden layer become some sort of input layer, right? And the connection, you have the fully connected weight between hidden layers and the output layers. So we got 12 weights, okay? 3 times 4, which we organize in a matrix. So it's the same math again, because the feed forward, you multiply this weight matrix with this hidden layer activation. So then you compute how much you should sum up the hidden layer. Okay? And for the output layer, for NLP, most likely it's gonna be a classifier. Then you softmax over that. And then you get the probability distribution over the labels. That's it, feed forward neural net. Do you want me to repeat what I just talked about 20 minutes over the past 20 minutes? All right, so this is the entire model, okay? So the model will have how many parameters? We have this as a parameter, right? WH, because the connection is between the input layer and the hidden layer, and WO, which is the connections between hidden layer and the output layers. And this is the bias term, also need to be trained. But for the output layer, I leave out the bias factor, but you can add that in as well. So WH is a parameter, WO is a parameter, B is a parameter, okay? And X is the input, usually embeddings that we saw before, and Y is the probability distribution over the labels. Make sure you understand different components of it because we will keep referring to these, okay? So a lot of vocab in one day. And after all of those, you can write the entire network in these two equations. All right? Yeah. That's it, feed-forward neural net. How do we use it for NLP? Cool. So one way to do it is to say you want to do what? Sentiment analysis again. So you can hand design any feature vector and use it as an input. So if you have review like dessert was great, for example, you could use some really simple feature vector like this one too. You count a number of words, not x1, and the number of positive words, great, right? So it's equal to 1, and the number of times that you see the word no, that's x3. So you can hand build, so you can hand craft the features. You don't do that much anymore, but sometimes this is useful actually. So you could make a feature vector as an input vector. So in this case, it's only 3 features connected to the hidden layer and connected to the output layers. Okay, so the way we use it, usually this guy, right? We try to find the right input for the document that you try to classify, and the output layers usually represent the labels, okay? The probability over each label. Yeah, so far so good. Yeah, let's go. Okay, so we learned about embeddings. So one really good model that we could use, and it uses embeddings, is this thing called, do I have the name for it? It's called averaging network. How do we do that? So first, we turn each word into the embedding. So it's the embedding that we trained, at the beginning of this period, right? Yeah, an hour ago, we talked about how we train word embedding. Suppose we train those. Once we train those, now we can use it for the classifier because the embeddings have some sort of meanings encoded, embedded, right? Embedded into the word. So what we do then is to substitute each word with the embedding. So we look it up, okay? Look it up in the embedding dictionary. So your embedding dictionary looks something like this, right? Okay, so we just now that we have trained it, now we're going to use it in the classifier. So train embedding, and yeah, we'll talk about others. So you average that, okay? So average over these embeddings, and then we use it to represent the entire text, okay? This entire sentence, and again we use the same trick. So connect it to a hidden layer, and then connect it to the output layer. The output layer will compute the probability over over each label. Do we have the result for this one? Okay, let's talk about this model a bit. This is a very good baseline actually. So I'll ask you to, for the next assignment, you will train this model, okay? And this is a very good baseline because you do almost nothing. Embeddings, somebody already trained that for you because you can download that and then use it directly. And averaging is so easy. So what's the reason why it can be just average embeddings? The answer, I can give you the answer. The answer is so unsatisfying, highly unsatisfying, because we did that and it worked. Is there any justification? Sort of. They said you can usually, if you want the compositional meaning of a text, you can add it up. They actually show that in the original paper. So it has a mild additive property, but then you add it over 30 words. One sentence usually have around 30, 20 words. When you add up the entire sentence in this fashion, there's no justification whatsoever. Okay? So once again, in the beautiful world in NLP, we use a lot of ugly things. This model included, okay? But it worked, so that's awesome. Okay, what about this hidden layer thingy? This one actually sort of makes sense. So hidden layer, we also call it a feature extractor. So you try to essentially reconfigure the input layers. Okay, so you want to use a combination, the different combinations of the input layer and to use it as a feature. So this might not be close to meaning because you just add up a bunch of embeddings, but the hidden layer will come to your rescue, will try to redo the embedding, usually try to compress it. Usually hidden layer is smaller than the input layer, so that you try to force the model to compress the feature vector to be something smaller so that you only have the signals. And you probably notice how much hand gestures I'm using here because it's never proven, okay, that it actually works as so. So when you see somebody try to explain something to you and they use a lot of hands like this, you can suspect that they are not very confident. They might be BSing you, and I am doing that. Okay, so this is what we hypothesize that it's doing. Okay, so this acts like a feature extractor. Again, we don't know that. And why do we add hidden layers here? So that's our hypothesis. Say again? We don't just believe it, right? We believe it and then we test it. So we add it there because when we add hidden layers, it works better. We don't know exactly why. We have a hypothesis of how it works, but we don't know exactly why. And sometimes we add more than one hidden layer and it actually works a bit better. Okay? The paper, I can just talk about it a little bit. The paper that make deep learning become part of NLP again is that they add 7 hidden layers. That's back in 2015, 2013 or so, not a long time ago. So neural network is a really old model. I said that before, right? But so people haven't looked at it in a long time because we believe that if you want it to work really well, you must add a lot of hidden layers. Once you have to add a lot of hidden layers, you have to multiply matrices many times, right? If you have 6 hidden layers, you have to multiply the matrices six times. And we didn't have good computers for doing that. And then some smart people at, I believe, McGill, Toronto and Google, they have a good computer. They use GPU for the first time to multiply a bunch of matrices, and then they can prove that this is a very fruitful direction for NLP models, and they were absolutely right. Okay, so from many hypotheses about the model, we get to where we are. But again, this is not a history course. This is the basis of all models that we are using now. All right. So you might see somewhere else that they use different notations for the model. So usually when we use feed-forward neural network, we do it for all instances. Okay. So if you have 1,000 rows, then you pack in all the embeddings, so the input feature vector, into one matrix. So you get an n by d matrix, and it's a number of instances, say like 1,000 rows, and d is an embedding size, so 300, something like that, 200, or 2,000, something like that. Usually, what you would use. Okay, and then to connect it to the next layer, you get the d by k matrix. D as in the embedding size, right? And k is the number of hidden units. Usually k is less than d, but again, you can do whatever you want. But these are things that we believe work well. All right. And once you have this matrix, we use this notation, W sub ij, which is the weight between xi and hj. Xi is the ith unit in the input feature vector, and hj is the jth unit of the hidden layer. And you see this more often, x times w, because it's more convenient. You don't have to transpose anything, but just so that the matrix dimensions agree. Okay, so you get the n by d times d by k. So when I think about matrix multiplication, I think I cancel this out. These must be the same, and the output is, when you cancel this out, then you have n by k. Okay. Yep. And plus b, and b is a bias vector. So yeah, when you look in the textbook or most papers, they will use this notation. I give you this so that you're not confused, or you're not like, oh, Ajahn just gave me a different model. It's the same. It's that you can transpose this and make it the same. All right. All right. Let's talk about training, so we can work on some lab thing this afternoon. Oh, how many more slides are we? Oh God. Okay. We'll have a break between. We're not gonna go through this before a break. All right. Training neural network. So we know how it works now, right? In a feed-forward fashion, you multiply a matrix, activation function, blah blah blah, and then get to the output layer. So to train it, so we have to train all the parameters once again, right? Including the embeddings, by the way. So the embeddings can also be adjusted at the same time. So to train a neural network, we want to find the ways that optimize loss functions. Again, the same thing we have seen. So we're going to use the same technique, but different loss. All right. So first, we will define a loss function that measures the distance between the system output and the gold standard output. This should not be new, right? What is this? This is softmax. Softmax gives you what? Probability of label C, where C is the correct class. and you take the log because so that the number looks nice. It's in the nice range. That's why you take the log. And we take the negative because we want to minimize it. To minimize the negative, you maximize the positive. So it's the same logic that we did before, okay? Computing something, take the log, take the negative of it. So it's the same cross entropy loss that we saw in logistic regression. So this is a review. This is not new. All right. So we can keep expanding these terms where y sub k is the gold standard label. All right. And so it's 1 or 0. So if k is the correct label, then y sub k is equal to 1. All right. And y hat of sub k is the probability that the network computed for you. So this should not be new as well. Okay. So when you take the gradient over this weight from I to k, k is the output layer, I is the hidden layer, right? Then you get something like this, which should be understandable to you now, right? This is the error. This error. This is the probability that you actually predicted out. So you take what? The difference between 1, 0 minus the probability that you predict. This is the same thing from logistic regression, exactly the same. Okay, and xi is the feature value of the feature vector x of unit I. Cool. So again, we use the error to use as a gradient. And this is a gradient. This is a gradient that we will use to update the word weight ki. So we use something like this, okay? So we can use gradient descent to update it. But today we will look at different optimizers that do something smarter than this guy. But what they all have in common is that we will compute the gradient, and the gradient has errors in it. That's why it works. Okay. So first we'll use the gradient, but we would not use this equation anymore because it has certain. What am I doing? Oh, okay. Oh, we talk about that after this thing. Okay, cool. Computing gradients. Now, computing gradients is a bit harder because now we have a lot of parameters that we need to compute the gradient for. So if you have 100,000 parameters, you have to compute the gradient for all of them, okay? Because you're gonna update each parameter with its own gradient. Okay, so now then it becomes a bit harder because then you need to compute the gradient for each parameter in this matrix, which is the connection between hidden layer and output layer, and the gradient for x and the connection between input layer and the hidden layer as well. So we have to compute the derivative for all of those, the gradient for all of those. And if you do it in the straightforward way, it would be really hard. But now we have a good library that does that for you as well. But I want you to see a little bit of the inside. Speaking of library, it does automatic differentiation for you, so you can compute any loss. You can set up any model that you want from the library, and it will compute the loss for you, compute the gradient for you, and the update parameters for you as well. Okay, so some cute, smart things. I want you to see the process, and so that you see why we need to compute all of these things to train it, okay? And that will have the repercussion on how you use the GPU cluster as well. So suppose you have this really complex function, very complex, c times a plus 2b. So what the computer actually does is that it will parse it and make a small computation graph. So to compute this, you need to compute this, right? You have some intermediate variable, a plus d, and what are a plus d? So d is equal to 2b, right? So you have to compute this first. Once you compute this, then you compute a plus d. So inside the brackets out, right? That's what we learned from grade school. And yeah, so to compute this, you need to look at the dependency in the computation graph, right? And then you solve each thing before you can get here. So to compute this, then you to compute this first. All right, cool. So when you know the value of a, b, and c, we call this forward pass in the computation graph. So you can compute the value of this function, and you do it in this order as well, according to this graph. Okay, so you pass the answer from one node in the graph to the next node in the graph, and at the end you should get the answer back. Why are we talking about this? So it turns out once you have this kind of computation graph and you want to take the derivative, to take the gradient over a, b, and c, you can do that very efficiently. To do that efficiently, so here's what you do. So first, you take the gradient of L over all of the variables that it depends on to compute the value of L, right, from this computation graph. It depends on what? It depends on E, right? E equal to A plus D. Then you take the partial derivative over with respect to E. Very easy, right? This is not very hard. This is not very hard. And then if you want to, for this guy, you want to take the derivative, the partial derivative with respect to D, then it's equal to the derivative of L with respect to E, which is what you pass on to here, right? And then also the derivative of E with respect to D, which is this guy. So which means you pass the gradient backward in the computation graph. So to take the derivative of this variable, you multiply up the derivative that you pass on from all the way back to all the way front in the computation graph, pass back to the parent node, and then pass back to the current node. And this guy should look familiar to you. This is chain rule in multivariable calculus. Okay, so L is going to be your loss function, but obviously it's much more complicated than this guy, right? But this is an example. So to compute the derivative over each parameter, right? E is a parameter, D is a parameter, A, B, and C is also a parameter. We have to take the derivative, the partial derivative over each variable, right? Diff of L, dl by dA. I think that's how you say it in English. I haven't said that in a long time. dl by dA, dl by dB, dl by dC, dl by dE. It's not very hard right here. So dl by dE is very easy, right? So you take the partial derivative of this function with respect to E. You can do that, right? So you get what? Get C, right? This we can do. And C is equal to minus 2, right? So you get dl by dE is equal to minus 2. So all the way back here, so you can apply chain rule for this guy using the computation graph. To compute dl by dA, it depends on dl by dE, right? And dE by dA. No, dl by dE, dE by dA, which we compute right here. So to get dl by dA, then you use a gradient from your parent, which is E, right? dE by dA, right here, and dl by dE, which we already computed. What about this guy? What about this guy? So it depends on what? dd by dB, dE by dA, and dl by dE. So you use this gradient that you pass down, this gradient that you pass down, and this gradient that you pass down. So this is the backward pass. So all I want to show you right here is that you can reuse the gradient that you used right here, right? You already compute that to plug in right here to find the gradient of this guy, right? This is already computed, right? EA, this is already computed as well. So you multiply this guy with this guy. So you don't have, so to compute this, you don't have to recompute these partial derivatives again. You can reuse those. This one is easy, right? Because C is already in here. So you could just take the partial derivative with respect to C and you get 5. But for this guy, where that's deep in the graph, the input layer, deep in the graph, then you multiply up the gradient that you compute upstream. Okay? This is the kind of thing that we're going to use, okay? This is the actual computation graph that we use, right? So this is the hidden layer, okay? So to get the Z, you you dot product, right? Weighted average between x1 and these weights, and you get the Z, and you pass on to what? Nonlinear activation unit, and then you multiply it by, no, this is the next layer. So this is the first hidden layer, right? And then you connect it to the output. This is the output. Yeah, and then you connect it to the output layer, right? You weight these two using these weight, and then you sum it up. Activation using sigmoid, and that's your loss, right? So all I'm trying to say is that, so first you find the derivative, you take the derivative of loss with respect to what? These guys, right? These are your parameters that you use to compute this guy. So, and once you have the gradient, right? So you pass it on to this graph, and to this graph, and to this node, sorry, into this node. So you reuse the gradient with respect to this weight to compute the gradient for this and this. Oops. Okay, these as well, but we will use different gradient, okay? So you compute the gradient with respect to this guy and go back in the graph. And to compute the gradient with respect to this guy, to this parameter, then you use this as well. This weight as well. Okay, it go back for bias as well to compute the partial derivative of the loss function with respect to this guy. You trace back from the graph, and you already compute the gradient of this. You're gonna pass it down to this guy to compute the gradient with respect to this bias term. So this, we call this algorithm back propagation. Okay, backprop, that they say for short, because you propagate back the gradient from the output layer to the hidden layer and to the previous hidden layers, so that you save the computation. So that's backprop. All I want to talk about is backpropagation. Okay, and that's the very algorithm that we use to compute the gradient over all parameters in practice. the library that you use, PyTorch, which we use today, will set up an automatic, will set up a computation graph for you. So your job when you try to build a model is to build up a computation graph, which will do some of that for you. But you need to know what layer connect with what layer. That's what you tell it to do, okay? So you set up the model, okay, and set up the loss function, what computation that needs to be done. And it will know how to do backprop for you to compute the gradient. But to compute the gradient, this is the steps that you need to know. First, you need to do forward pass, as in you need to compute this guy when you use the training, when you use the training set. So that's why you need to compute the loss first. Once you compute that, then you can compute the backward pass. The backward pass, you compute the gradient from the last node in the graph to the previous nodes in the graph. Okay? That is also why when you want to compute the gradient for all these guys, you have to keep the values in the intermediate nodes. You have to keep these values around. You cannot throw them away. Okay, it's not that you compute the gradient and then you compute the forward pass and then you can forget the activation that you compute. You have to keep that in memory. Okay, and that's what the computation graph also does for you. It computes the forward pass activation, and to compute the backward pass activation, it did the backprop from the last layer up to the first layers. So this whole thing is called backpropagation. I should say that somewhere. I'm going to say that now. In neural network training, we call this algorithm backpropagation. Very important. Okay? Oh, tricks. Okay. Let's take. Can we go through this? It's so long. Okay, let's take a 10 minutes break and we'll come back at 2:37 and we will talk about optimization. Okay. Training, yay. So training neural network is kind of tricky because we do so many hacks. So it's gonna be, a bit tricky. How? So first, we use stochastic gradient, right? The training loop will look something like this. So suppose that data is a model parameters, then we, for each epoch, right? For each epoch, we iterate over each row in the training set. Again, we will compute the loss because that's a forward pass. Without a forward pass, we cannot compute the gradient. Okay, so the function that you use in PyTorch will look something like this. So you compute the loss function and then compute the gradient and then apply and then update the parameters based on the gradient that you computed. So this is stochastic gradient because to review, we compute the gradient for each row and then for one row and then you update it based on that gradient alone. So stochastic gradient, so we compute for just one row, and another term for this one is batch gradient, which means we compute the gradient for all rows and then you average that, which is fine, but it takes a long time, so we never do that. To give you some vocab, right? So one iteration, when we talk about one iteration, it means that we one update to all parameters. Okay, that means one iteration means forward and then backward. That's one iteration. Okay, it doesn't mean iterate over all these. Okay, it means this thing. Boop, boop. So one iteration. Okay, so one iteration you might compute the gradient over many rows, not just one row. Okay, so iteration means one update, one parameter update. And epoch or epic, depends on how you want to pronounce it, epoch or epic. One epoch is one full training loop. That means we look at the training set, all rows of the training set once. So that's one loop. We call that an epoch, okay? Or epoch, let's say epoch. Yeah, so one epoch. So what we do in practice is that we do mini batching. So we try to do something in between. So instead of compute gradient for all rows, it takes too much time. So we don't do that in practice. We will do something in middle, because computing gradient for just one row is not great either, because you might get unlucky. Your training set might be kind of noisy, or the sample that you computed gradient for might not be a good sample. It might have a wrong label, that's also possible, or it might not be representative of the training set. So you doing compute the gradient for just one is not a great idea. So we have something in between we call mini batching. So batch means the whole thing. Mini batch means a batch that is smaller. So mini. So you compute the gradient over multiple rows. So you can adjust this thing called mini batch size. So sometimes it's just called batch size. Okay. So if you set it equal to 3 and the number of rows in your training set is 15, then you have 5 iterations. Okay? So one epoch equal to 5 iterations. So when you train one epoch would be what the effect of training on one epoch would be very different based depending on your mini batch size. So if your mini batch size is so large, which is great because that means you get the gradient that is reliable. If your mini batch size is large, one epoch would not do much because you don't update that many times, right? So for example, in this case, if your batch size is 10, one epoch will equal to 2 iterations. So you update your parameters only twice. Okay, so that's not great. So sometimes it's hard to say how many epochs you need because it depends on the mini batch size as well. Speaking of mini batch size is very important because it also determines the accuracy that you get from the model as well. If it's too small, then you are more like stochastic gradient descent, because you might be again unlucky and sample bad samples from the training set. Then you get bad gradient, your parameter will be worse. Okay, so if you average over a larger mini batch, say 64, 32, then that's great. Why is that great? Because if you get some, or hopefully just a few bad samples, you average over the good ones, then you're good. Okay, so mini batch size should be moderate, usually 128, 64, 32, something of base 2. Okay, what about the flip side? What if the mini batch is so large? Say, like a lot, like 2,000. Why don't we do that instead? Because, professor, you just said you average over many rows and you get a good gradient. Why don't you set the mini batch size to be very large? It would take too long to compute the gradient. So we get the same problem with batch gradient descent, right? Because this takes very long, although the gradient is nicer. So we try to do something in between. Okay? So it's weird. Why is it weird? Then we take the gradient over different loss function each time, right? For each mini batch, it's different training loss, because the training loss if you remember training loss, it it's defined over the entire training set, right? When you look at the equation. But in practice, we never take the gradient and average over the entire training set. This is a hack, once again, that works really well. So mini batch is here to stay. We are using it to train all neural network models. All right, another tricky part. So one tricky part is mini batching. You have to pick the right kind, the right size, okay, so that you can train it at reasonable time, and it's also converge to a good accuracy. Gradient descent. Once you get the gradient, you have to decide how much you're going to trust it, basically. So how long of the step size you want. Okay, so usually this is how it should go. Once you have the gradient, when the cost or the loss function changes very fast, so means you are far away from the optimal point, so you should go fast. So when you first train the model, you get crap. Oh, sorry, that's not very nice. Then you get not so good parameters because you just randomly initialize it, right? So which means wherever you are, your loss function will fall really quickly because you're so far away from the optimal point. So you should go really fast from the beginning and start going slower toward the end, taking smaller and smaller steps toward the optimal point. But I show you right here that alpha in stochastic gradient is a constant. So it would not have that property that we want. So the alpha would be either too large or too small, because it would be too small at the beginning and too large at the end. So that's not great. So we have other optimizer. Oh, this, yes, I just said that. So if step size too small, you have to update way too many times. So you have to compute gradient many times. That takes too much computation time. And if the step size is too large, then you will oscillate. Oscillate means, this is oscillate, okay? And you never get to the optimal point. You keep jumping back and forth on the cost function surface. Okay, so not great either. So we have something in between. That's why training neural network is about like knowing that right value for training. So we get something quite smart actually. You guys are required to take optimization, right? Yeah? Yeah, right? Oh. So here's optimization for you. So you get that illusion of choice. I'm just kidding. So this is the only time that we're going to talk about optimization, okay? So I'll talk about 3 optimization algorithms. They are designed almost specifically to train a neural network. So momentum, the first one, momentum. Momentum, here's the intuition of it. Next slide is math, which is ugly, but I'll explain that to you as well. So suppose, so you're going to compute the gradient many times, right? Because you're gonna pick a new mini batch, compute a gradient, update, pick a mini batch, compute a gradient, update. So the gradient that you get from each time will be different. Here's what momentum algorithm takes advantage of. So if the gradient that you have seen in the recent times, say the previous 3 times is small, then you should go small. Okay, so you should take a small step size. So the idea that they get is that you should just take the average over the past gradients from the previous 10 iterations, 20 iterations, and so on, okay? So you take the average over the previous time. So if you see that the gradient is getting smaller, the average of the gradient will be small, and the step size will be small, which is what you want. So you should slow down. Okay, so you see that it's not the gradient is smaller and smaller now. We should go small as well. And this guy, what's happening here? So if you see that the gradient start to oscillate now, so it bounces up and down too much, that means you're not in the smooth area anymore. You start bouncing around. You start to oscillate. You start going around. So if you take the average of something that oscillates like this, then you get the negative and the positive will cancel out. Then you get something small. Then you take a small step. So by taking the average over the previous gradients that you have seen, then you can make a more educated option on how to update, small or large. Okay, so on the other hand, if the gradient is so large, that means like, oh yeah, you can go fast, you can update very fast. So the average over the large things, you get a large mean, and then which means that you can trust the mean to guide your step size. Sorry. So the intuition of momentum is that you should take the average across the previous times, across the previous gradients. If it's large, then you take a large step. If it's small, then you take a small step. Yes. You see in the next slide. Scary stuff. Okay, not that scary, I guess. Okay. Cool. So, momentum algorithm, it computes something called velocity. Okay, velocity. So and g sub t is the gradient at step t. And vt minus 1 is the velocity of the previous time. And as per your question, how do you know that it is large or small? We have this thing, learning rate, anyway, to control that. So you can adjust at the beginning what is large and what is small. So if the large thing, you want it to be very small, you adjust learning rate to be 0.00001, so it will scale down. So this is how you deal with the magnitude of the gradient. Okay? And you have this beta, it's called decay rate. You set it around 0.9. And professor, you said you take the average. Where's the average? I don't see any averaging going on. But you can notice that this thing is a recurrent relation. So you can keep substituting Vt minus 1 with this term. Let me do that for you. So recurrent relation. So Vt minus 1 is equal to beta Vt minus 2 plus this guy, right? This is not so hard to prove, right? So all I did is that I expand this term, Vt minus 1, and that's is what you get, right? And you multiply beta into this bracket, and this is what you get. Does it look like averaging now? Sort of. This is gradient of the previous time. This is a gradient of the current time, right? And if you keep expanding Vt minus 2, then you're gonna see Gt minus 2 somewhere. And then you keep expanding Gt minus 3, minus 4, minus 5. And then you can write the velocity at times t as this term. Does it look like average now? Sort of, right? Sort of. But you know for sure that you sum across all previous times that you compute the gradient. And what is this guy? Beta k, beta to the power of k. So which means if k is large, which means it go way back in the past, right? It's not gonna matter much because beta is 0.9. 0.9 to the power of 10 is what? 0.09, right? It will be something very small. So we call this term exponentially because we have beta to the power of k. Decaying average because the farther away in time, it's gonna matter less. So we still take average over it, but not the same amount. We give the weight to the recent gradient more than the past gradient, than the distant past gradients. Does that make sense? So I hope you understand what velocity is as an exponentially because you take the power of k, decaying because beta is less than 1, so it's going to become smaller and smaller. Average of the gradient, average because you look at all of the previous time steps, and gradient is right here. Okay? So I hope you understand the connection between this sentence and this scary looking equation. Okay? So we write it out this way because once we want to compute the velocity at times t, the current time, the current iteration, we only need to keep what? The velocity of the previous time. So we don't need to follow over the past gradients. That means we don't need to keep all the gradients around from the first iteration to the current iteration because that's going to be expensive. So, yes. So, once you do all this thing, which if you look at the normal thing, it's very, very easy to compute, right? So you keep the velocity at a previous time, and you apply this equation once you get the gradient of the current time, and then you get the vt, and this is the normal stochastic gradient, update. So when you update not only from the current time gradient, you update based on the current time and the decaying average of all the previous times. So you have some memory of what you have done. Okay? So in this demo, the beta is the decaying rate. Okay? So so it will bounce around a bit, but usually we set the decaying rate to around 0.9 or so, and the step size set it to something small like this one, but they both matter actually, like a lot too. Okay, so now you know the right range of where things should be. Okay, let me ask this question. So what if I set beta, the decaying rate, to 0? What would happen to the algorithm? Would it explode? Would it collapse? Would it? Exactly. So the answer would be the same as stochastic gradient descent, because this term will go away, right? Once this term go away, we don't have the memory of what happened before because it's always 0. And 1 minus 0 is 1. So you plug this in, so become just theta t minus alpha g sub t, and g sub t is the gradient. It's the same as stochastic gradient. So it's very easy to show that. Yeah, so which means if the beta is low, is gonna trust the recent times more. Okay, so you're gonna let it decay, let the gradient from the past decay very fast. Cool. So if you use this algorithm, which is still applicable, you have to adjust beta and alpha to be in the right range. All right. Another smart person came up with another algorithm, which they claim to be better. It's called RMS prop. Here's the idea. So he said that maybe they didn't say exactly this, but the idea is this. Here's the intuition. So to update, you should not look at the average over the previous time. You should look at the variance, as in the variation. Because if the gradient is kind of the same, you could go fast because you're going down the same direction as last time. But on the other hand, if you get something like this, right? The variance is so large that means like you are bouncing around. You get the gradient that they are not the same each time. Since they bounce around, so you should take smaller step. Okay? For this guy as well, right? You can see that it go the very small should be very small. It should be large as well. Sorry. Large step as well. So you can see that we should be going fast as well because the gradient is in the same direction. We are going down the same direction as last time. So compute the gradient next time would not be that much different. So we should really trust this update. Okay? So the intuition then is that if the variance of the grade of the previous times, as in it's kind of the same, is small, then we should take a large step. If the gradient is all over the place, it keep like bouncing around, then the variance is large, then we should take a small step. Okay, so like different intuition, right? The momentum, they said trust the mean. The mean should tell you whether you should go large or small. But for RMS prop, they look at the variance. If the variance is small, you should go large. If the variance is large, you should go small. So we're gonna use the same trick we used to compute the decaying average of the mean. Now we're gonna keep the decaying variance of the gradient. Does it look similar to you? Same trick, right? This guy with the recurrent relation, and instead of g sub t, you got what? G sub t square. Whoa! And we got the new name. But other than that, it's kind of the same. The VT is now in the downstairs because the larger VT it should update less, right? So they put it in the denominator. Okay, so the idea is the same then. Instead of keeping the decaying average of g sub t, of the gradient, we keep the running average of gradient square. See, alpha the same, right? Alpha is the same. Cool. Oh yeah, now we have this extra thing, epsilon. Epsilon in machine learning in stats, it means something very, very small. Why do we need something very, very small? Because we don't want this to be zero. Because then you don't want to end up dividing something by zero, because then bad things happen. When you divide it by zero, you get infinity. Then when you try to subtract theta t from you try to extract infinity from theta t, you get some stupid number that you cannot compute with. Okay, it will be a NaN, not a number. This is the same math, right? I just replaced g sub t with g sub t squared, but the recurrent relation is the same. This equation is even the same. But again, I replace the gradient with the gradient squared. What if beta is equal to 0? Then it's the same algorithm as before. It becomes stochastic gradient as well. Eta grad. I'll skip eta grad actually. All right. Here's what we actually use. It's called Adam. So Adam, what it did is, I want you to look at this equation first, the update equation. Remember this guy? This guy is from here. Square root of v sub t is from RMS prop. And this is what? Remember this term? This is momentum, right? This is the running average of what? Of the previous time in the gradient. So this term here come from momentum. This term here come from RMS prop. You just combine them together, nothing new. And for the sake of completeness, they don't use m sub t directly. They correct it a little bit by dividing by 1 minus beta t right here. But this is so not important. The idea that I want you to get from Adam is that it uses both average gradient and use both variance of the gradient over the previous time steps. And it turns out this idea works really well, better than the previous two. So optimization done. So the code becomes something like this. Neat batch. Okay. Sorry. Okay. Yeah, to be clearer. So here's what your PyTorch code, which is the library that I'll let you play with for the rest of the class today, so that you have more time to adjust to it. So for, say you want to train it for like 2 or 3 epochs here, okay? And then the code will go something like this. First you initialize the optimizer. It can be like Adam, it can be like RMS prop momentum, right? So first, again, compute the loss, that's a forward pass. And then you compute gradient, that's a backward pass. See that you have to give it the loss right here, right? And then what? You have this step where it updates the statistics. What statistics? This guy, right? It has to update based on the new gradient that you just computed. So that's what this step means. Okay? Don't forget that. Don't forget this one. After it compute all that, then you can compute the learning rate for each parameter. So this guy. Okay? This guy. And then you can apply the usual update equation, which is the theta minus alpha times the learning rate that you compute in a very sophisticated way. Okay? Good. Okay. There's no definite answer on which one is actually the best. There are a lot more optimizers actually. If you look online, if you ask ChatGPT, it will give you AdamW, it will give you Ada Boost, it will give you Ada Grad, and many others optimizers. So a good thing about this is that there's no definite answer on what's the best one. Everyone has their own favorite optimizer. So if you ask like other professors or other AI engineers, they were like, I like Ethergrad. I like people don't know that RMS props actually the best. Everyone has their own favorite favorite optimizer. For me, it's Adam, by the way, if you want to ask me. Again, there's no real justification of which one is better. But all I want you to understand is that it uses the idea of the previous gradients, either in terms of the decaying average or the decaying squared gradient, which is the variance. Okay, that seems to be the theme. There are many others optimizers, but all it does is to make a variation, create a variation of these statistics over the previous time steps. Okay? Good. Oh, I have mini batching right here. Okay, good. Sorry, let me change that back then. Yeah, we will use that with mini batching, and that completes the one whole idea of training neural network. Oh yeah, cool. A popular question. So how many epochs do we need? So when we talk about training, we usually talk about it in terms of epochs, right? So how would I know? It really depends. We talk about the mini batch size already, right? Like if mini batch size large, you don't update as often. And it also depends on the optimizer as well. If the optimizer gives you really small step size, then you need to update a whole lot more times. And also it depends on the training set sizes as well, right? If you have really large training set and your batch size is 32, then one epoch gonna take you a whole lot longer because you have more iterations. So it depends on so many things. So I hope you see the big picture of what makes a good model, what makes a good training process. There are many factors, right? I said mini batch size, training set size, the number of epochs, the learning rate and the decay rate in the optimizer. So these all have matter to the accuracy rates. Thankfully though, we have something that help you track the training process a bit better. So the question becomes, when do you stop? Because the number of epochs would matter. So there are three signals, and three signals are the same. It signals when you make no more progress by updating more times. So you look at training loss, validation loss, and performance metrics. Training loss. When we look at training loss, we look at the loss for each time step. For each time step, yes. Okay, so you could either compute it for each mini batch and look at it right away, or you can compute it for the entire for each epoch as well. Then it would be easier. Okay, so this is a typical training loss. If you train today, I'm gonna give you some time to train neural network model. If it doesn't look something like this, something is very wrong. Okay, so it's either you don't set it up right, you didn't clean the data, or the learning rate too big, too small, something. your training loss should look something like this, should be quite smooth. So these are real, by the way. I pick out from other projects. So it should go up and down a bit, but it mostly down. Okay, because auto optimizer are usually quite good, and if your training data is not so abysmal, then it should be fine. So you should see something like this. Okay, if you see something like this, that means you're doing something right. So you get some decent classifier. So it would drop really fast at the beginning. This is very typical because you start somewhere not so great, right? You start with really bad parameters. So you update it quite a few times. You get something much better than the random parameters that you got at the beginning. And how do you read the signal then? It should flat out at the bottom, because then that means your update doesn't matter to the loss anymore, so you should stop. Okay. Cool. So in machine learning, we call this point overfitting, because you can keep adjusting, updating the parameter so that loss will keep going down. The loss will keep going down, by the way. You cannot just say stop when loss stop going down. It will go down, but it will go down very slowly. That's when you know it's not that great. But again, the question would be, how slow is slow, right? So training loss is okay, but we got better things. So we will look at other signals as well. It's validation loss. Going back to the first period where we first met, we talk about 3 chunks of data sets, right? Training set, validation set, and test set. This is where you use validation set. So every once in a while, every 1,000 iteration, every 1 epoch, every 100 iterations, whatever have you, you're gonna compute the loss on validation set, which is great because the algorithm is never trained on the validation set. So this is a very good signal for us. So it's a proxy for how well it generalizes, as in how well it can capture the data that it hasn't seen before. Okay, so this is a better signal than the training set. In this example, I'm quite lucky that loss, this is real curve, by the way. It didn't just like put it in Excel and plot it for an example. This is when I train an actual model and test it on validation set every epoch. It would not look something. I try to make it look less nice, but this is what I got. So this is what we see. So it will go again. It will look like training loss, right? It will go down quite rapidly at the beginning, and then it will flat out toward the end as well. So that's great. Optimizers these days are really good. So your loss, validation loss, will look something like this. When we don't know much about training neural network, it usually looks something like this. So which means it will start to get worse right here, right? That means when you update way too many times, but I think the optimizer did a pretty good job here to make the update to make the update so small that it doesn't overfit to the training set. So if you get something like what I saw right here, that's awesome. Okay, it will look something like this. Cool. All right. This is the third signal. This is the one that we try to rely on the most, but we use all 3 when we train neural network. This is validation set. So on the x-axis is the number of the number of iterations that you have updated the parameter, and on the y-axis is the F1 score or the accuracy score. So this one, then you look at it and then you are more, then you feel happier because you know that you're, you see the F1 score, you see the accuracy, you know how well it works now. Because loss, what does it mean to have a loss of 0.7? It means nothing. It means nothing at all. But the accuracy is great, right? You know that, oh yeah, now it's at 76% accuracy, and we like that. Okay, so this is what we would use in general. We every once in a while we compute F1 or accuracy on the test set and validation set, and see how it changes. And this is quite typical actually, to see it flattens out quite quickly toward the end. And sometimes I try to make it not look so good like this. Usually you see it drop slowly as well. That's usually what you would see. That's when you think you should stop around here, right? That's when the accuracy of F1 is the highest. Okay, so that's when we know how to stop. Okay, and if the result doesn't look good, you go back and change things like mini batch size, and the number of epoch would change as well. The number of epoch that you require would change as well. So part of the training process, you always want to validate your model on the validation set. This is also why you don't want to you don't want to use your test set, because you ended up yourself look at the validation set many times, right? For for each epoch, you already try to optimize over that. And you also use the validation set to pick the best model, right? The best model, you said, is around 800 iterations. So you use validation set to pick the model already. So we try to not use a test set for anything except toward the end, where you look at the accuracy for this guy, for the model at this checkpoint. Okay? So to put it back together, training set, you use it to update the parameters directly. Validation set, you use it in this manner. You use it to select the right checkpoint in your training trajectory, in your training process. Okay? And test set, that's when when you want to ask, like, this model, one, don't do it for all, just one that you already picked from the training process, how well it does on the test set. And that's the number that represents the true accuracy that you could expect. Okay, so that's the put it back with machine learning framework. Cool. All right. Let's look at what actually happens when you train neural network. And as per my tradition, we'll try to train neural network on spreadsheet. Not all the way though, but to compute the forward pass. Worksheet. Yes.
In this spreadsheet, can it do like derivative, like auto derivative to the spreadsheet, or that is beyond the capability of?
I don't even compute the derivative. No. We won't do the update here, but I want to compute the forward pass for you to see. Cool. So for those who don't read Thai, these are a bunch of words that are words. These are a bunch of words as well, and these words are in the embedding matrix right here. So the embedding matrix we use for converting each word into the embedding. Okay. So once again, when you want to process the data, you tokenize it, and then you convert it into the indices based on the embedding that you have. So for example, Nangam is on index 5. So you change from Nangam to 5. B is 9. 9 is right here. Ni is, where is that? 6. Okay. Something like that. Nia is like number 7. Soy is 12. And Ra is not in the embedding. So we assign it 16, which is embedding that's all 0, because we don't know what number we should give it. Okay, so we've got this vector. It become a vector of indices instead of a list of tokens. Okay, and notice that when you see in the real code pretty soon that you have to indicate what's the max length that you want to process the data. So how many words that a text is allowed to have. So which means 1, 2, 3, 4, 5, 6, 7. In this case, in this model we said we will process 7 tokens max. Okay, so if your data has only 6 words, we're gonna pad it. This is a technical term, padding. Okay, pad it so that each row has the same size. Okay, that's why I put the 0 here, because 0 is padding. And on the other hand, if your data set, if the sentence, if the text is too long, as in longer than what you specify, we specify 7, right? So we will look at only these 7, the first 7, okay, and convert it to the indices based on the embedding that you have. And this is called truncation. It's a big word for cutting something short. Truncate. Okay, so we had to truncate it. So now you notice that these 2 rows have the same size now. Yeah, so far so good. So this is the first step. So now we don't deal with text anymore. We deal with numbers now. So now that we have indices, then we convert it to what? Convert it to the embeddings. So we look up like 5, this is this vector. So we copy and paste it here. Okay, so we do a lookup based on the index. Yeah? Good. So then your data set is n by 7 at the beginning, right? Because you make these 2 into a matrix. And once you expand it, then you have a tensor. A tensor is a term for some matrix that has more than 2 dimensions. Okay, so it's n by n as in the number of rows that you're processing at the time, times the sequence length, which is 7, times the embedding size, which is 4. So at this point, your data set, your mini batch is a tensor of size 2 by 7 by 4. Okay? check this when you process the data. Make sure it has the right dimension, okay? N is the millibatch size. 7 is the length of the sequence of the sentence that you allow it to be. See, we have to truncate it into 7, right? We leave out two words. Not great, right? And then 4 is the dimension of the embedding. So when you set up the model, very important to check the dimensions. Make sure dimensions make sense. Most of the bugs that you get from the model will be from tensor dimensions, okay? Because training data, we have like tens of thousands. We're not gonna look at them. Yes. Say again? N? N is the size of the mini batch. So in this case, we are processing 2 sentences. So N is 2. So it's 2 by 7 by 4. So this is 1, this is 2. And yeah, I think that's the hard part that I'm going to talk about, because I want you to have 20 minutes to work on this thing. I think should be good. Okay, so what I just posted on my course reel, it's a lot of questions that I essentially give you all the code for PyTorch for implementing this model. Okay, the averaging model. Yep. Okay. So do tokenization. If you run it, it should work from the beginning to end. What I want you to do is to answer these questions, which is annoying questions, because then you have to go through each line and know what it does. So go through line by line and like figure out what each line does, so that you have the entire step, the entire process down of how to train a model. So first, you have some sort of tokenizer, right? So to tokenize a model, and this is to convert it into X and Y. And this is where you set up the model. So you have the embedding, connect to the linear, and have the activation function, and its output layer, and so on. Okay, so the code already works, but I think if you read it, or if you ask ChatGPT, then you should get a clearer idea of what these all do. To load up the data, put it all together. This is the training loop that I told you about. Okay, there's a backward, forward, backward step, and compute the loss on validation set. And that's all the code does. But I'll give you the rest of the time to answer all these 16 something questions. Okay. So just give me like very short answer. Don't give me something lengthy. What's the purpose of this? How are they initialized? Do the best you can today. Yeah. Do the best you can for the rest of the day, because I already give you all the code. You only have to read through it. Okay. And again, this is not like homework, so do what you can with the time you have now, and I'll yeah.